All right, so I've got a piston cylinder fitted with a set of stops. There's water, 2 kilograms of water in that piston cylinder. I'm given initial temperature and pressure. I'm told that it undergoes a compression process to a minimum volume of 0.2 meters cubed, and of course the stops prevent that piston head from moving below that mark. And then it undergoes another process where the temperature of that water is cooled further to 170 degrees Celsius, but the volume remains constant because those those stops are present. Then I want to find the work and the heat transfer from states 1 to 2, and then the heat transfer and the work from states 2 to 3. And then I want to draw both processes on a TV diagram together, clearly labeling all the relevant information. So the first part is to find the work from 1 to 2. I only have compression work due to compression, to a volume change. That's my boundary work. And I have an equation that I can use, a very simplified equation, which I need to assume that compression process happens very slowly, and so it can be modeled as a quasi-equilibrium process. The pressure is constant, so it comes out of the integral, and I just need to look up what V1 and V2 are. V1 ends up being in the superheated region. So at P1 and T1, I can look at my thermodynamic tables and verify, yes, I'm superheated, go to the superheated tables, pull off that V1 value, and then move on to V2. V2 is really easy because I'm given a volume and a mass, and so I can directly calculate the specific volume. And I can plug and chug and get a final work from 1 to 2 of negative 206.61 kilojoules per kilogram. Part B is asking for me to find the heat transfer, and so I'm going to apply the first law for a closed system. I'm going to ignore kinetic and potential energy changes from 1 to 2 because I don't know anything about it anyway. I'm going to bring the work over to the right-hand side of that equal sign, and then I'm going to look up U1 and U2. Once again, state 1 is superheated. I already verified that, and so I can look in the superheated tables and pull off that U1 value. U2, well, the two independent intensive properties that I know are pressure, 10 megapascals, and the specific volume that I calculated in part A, which is 0.1 meter cubed per kilogram. So it's saturated, which means that it follows this equation right here. U sub F plus the quality at 2 times U sub Fg, or you could write that as U sub G minus U sub F. So I've got my U sub F, I've got my U sub G values, and I can pull those out of the saturated tables at 10 megapascals. I need to solve for my quality, but I know that I can use my specific volume for that. So the specific volume follows the same relationship. V is equal to V sub F plus your quality times V sub G minus V sub F. So I just rearranged that equation right there to solve for my quality. I pull off the V sub F and the V sub G values off of those saturated tables at 10 megapascals, and I get 0.512 for my quality, 51.2%. I plug that into my U2 formula, and then I use that U2 value that I just got to calculate what my heat transfer is from 1 to 2. So now I'm good with that. I need to find part C, the work from 2 to 3, and that's really easy because the only work that I might have going on here is due to the compression process or expansion process that might occur, and I have no volume change from state 2 to state 3, so my work is clearly 0. And then for part D, I need to find the heat transfer from 2 to 3. So I'm going to apply my first law. I'm going to get rid of the kinetic and potential energy changes. I'm going to bring the work term over to the right-hand side, which I already calculated for in the first place. It's just 0. And so I need to get U2 and U3. Well, I've already got U2. I found that out in the previous problem. I do need to get U3. So I've got T3, and then I've got the specific volume at 3 because, well, the specific volume, the volume at 2 and 3 are the same. The mass is the same at 2 and 3. And so the specific volume is the same at 2 and 3. It's that 0.1 meter cubed per kilogram. And if I look at 170 degrees Celsius in the saturated tables, I can see that I'm firmly in that two-phase region. So I need to calculate this based on U sub F and U sub G, and let's see, need to use my quality once again to calculate use my specific volume to figure out what that quality is, and I get 0.4095. Then I plug that in to get U3. And then I plug that in to get my heat transfer from 2 to 3. So I'm good for part A, B, C, and D, and then I just need to draw things on a TV diagram. This is part E. So what you see here is you see my vapor dome. State 1 is clearly in the superheated region, and state 2 and 3 are in the two-phase region. Now from 1 to 2, you note that we had a constant pressure process. So that line that goes like, let's see, zoop, zoop, that's a constant pressure line. So it would go, right, it kind of slants like this on the right-hand side. It goes straight across in the middle, and then it would go like this once it got to that saturated liquid line. So from 1 to 2, clearly going along a line of constant pressure, and then from 2 to 3, the volume and the specific volume are the same, don't change, I'm sorry, from 2 to 3. So the specific volume at 2 and 3 are equal to one another. I've labeled what the specific volume at 1 and 2 and 3 are on the x-axis, and on the y-axis I've got my temperatures. Now T1 and T3 were both given to me, but T2 is not. Now the way that I got that was I just said, I said, well, because I'm saturated at 10 megapascals, then the only temperature that I could be at is the saturation temperature, and that's 179.9 degrees Celsius, and I get that from my saturated tables. All right, well, I hope that was helpful. Thank you for watching, and let me know if you have any questions.